Okay. You guys got an answer already?
Yeah.
For A1?
Yeah, 8.1 part A.
Part A, which is finding I of 0 plus and V of 0 plus.
Yep. So this is an open circuit, which means there's like a break here. And this is the short circuit, so there's a straight wire. So this reduces down to this circuit. And then if you want to find I, you do I equals V over R, which is 12 divided by 6, which is 2.
Okay. And what's V?
12.
We have to square them.
There's only one
voltage
source. That's too bad I have the answers there. That gives you a false sense of understanding.
The difference.
I like to not.
Yeah. Can you just
because you can just say, oh yeah, it must be this because of that.
if you're looking at VO minus, which is just this circuit, it has to.
Yeah,
12 volts.
That's cool. Now, the more challenging one is going to be the hardest one of all of these is always the derivatives. The final value is pretty easy, but then the derivatives are going to be a little trickier.
So when you draw this at t equals 0 minus and t equals 0 plus, since it's steady state, are you always going to assume at those 0 minus and 0 plus values it's going to look like this? Because
what do you mean? Well, always. What do you mean by always?
Because we're always going to assume that the inductor is a short circuit and the capacitor is an open circuit.
That's for minus.
Yeah. Yeah.
Isn't that for plus too, though?
Well,
Since
plus,
it's the same thing.
if it's plus, then that's going to be open. So this 12 volt goes away. So it's just that circuit.
Oh, true. Okay. I think
when it's plus, they basically retain the values they had when it's minus, but they're no longer necessarily open and short.
But if we wanted to find at t equals infinity, then we'd, I guess, get rid of this and we just have this whole thing.
Yeah.
Okay.
So if they want to find DI, DI 0 plus, we'll be looking at the circuit without the 12 volt in it. We'll be finding the current through there.
Yeah, that's when you, so that's when you go basically. So yeah, kind of what Matthew's saying is, when the switch is closed, this is an open circuit and this is a short circuit, right? When the switch is open, you can think of this as being, this is going to now be like momentarily going to be like a current source with the same value it had at 0 minus. This is going to be like a voltage source with the same value it had at 0 plus. It's no longer going to be an open and short circuit necessarily.
Okay.
It's going to just hold on to those values that it had in the previous moment.
You said that's when the switch opens?
At 0 plus.
At 0 plus.
The switch is opened and those things are holding on to their former values at 0 minus. Those are the only things that are guaranteed to not change. Everything else in the circuit could change. Yeah, so some books show drawing a drawing it as a current source and a voltage source.
Yeah, that's what I was saying.
That can be really helpful. Then you just have to find. For DI to T, you got to find the voltage across the current source, and for DV to T, you got to find the current going into the voltage source, or with capacitor that has now looked like a voltage source.
With the diagram now looking more like that.
Like that, yeah. Where that 2 amp source is the inductor and the 12 volt source is the capacitor in 0 plus. So you put like T equals 0 plus right there. That's really, in that moment of time, that's what you're trying to find. Yeah, so
can we take that approach on a lot of these problems when we're trying to find something at t equals 0 plus? Or
sure.
Those things are current sources, voltage sources.
Yeah, you can do that. Okay. That's something that I was telling. There's some site that kind of shows you how to do that. It's kind of helpful. Okay. Draw it that way.
So the voltage just be 12 volts because it's 6 times Q or no?
No, because you got 2 amps. You got 2 amps going through. You got to do KVL. You got 2 amps going through that loop, right? And you want to find, so you could call this, VL. You can call this IC, and then solve for those using KVL or KCL, whatever. right. How's it going over here? You've got, yep, you got the open circuits. There we go. Yep. Now you're trying to do the derivatives, right? So 0 plus.
Okay.
Yeah, 0 plus, this is a, yeah, you've drawn that as a voltage source. You could sort of draw this as a current source of 2 amps too. It's actually not a short, really, at this point. It's a short at this point. But at this point, it's going to be pumping the same 2 amps that what it's doing at 0 minus. Yeah, so you could draw it like that. And then IC would be flowing into the plus side of the capacitor, and then VL would be the voltage drop across that. And you can use those to find the derivatives. Yeah, just drop IC going down. Yeah. Yep. So you solve for those, and then you'll find dVc dt and dIL dt. So you are doing the whole shebang one, right? That's the, you got to do the whole thing, right?
I don't know what that means by the whole thing.
Yeah, you got to find everything. Yeah, these are all like pieces of getting, started on a problem. This is the whole thing. So you're going to look at this and you're going to say, well, this is a, is it a series or parallel?
Series.
Yeah. Series, is it source free or step?
Source free after
Yep.
the.
Mm-hmm.
So it's just a source free, yeah. RL series, right?
Uh-huh.
Should be pretty easy then, right? Should be pretty simple. After
Well,
two.
yeah, you just got to do all those initial conditions and all those things.
We might need more space. Yeah.
Yeah, you could probably move into this area.
Yeah, so we're gonna need
Any questions? So what you have to find, Alex, is you got to find VL, because di dt, because V equals L di dt. So di dt equals VL over L. So you find VL
Okay.
and divide by L, and that's what that's going to be.
All right.
For the capacitor, for find dV dt, because I equals C dV dt, then dV dt equals I over C. So you got to find IC going into the plus side of the capacitor. So you can label those on your diagram. You can label VL, yep,
VL.
and label IC. Yep.
Yes, I did.
This is wasn't it
IC over C.
Yeah.
No.
Okay.
And so we're going to find the derivative of yeah, VL equals what LDI, so by KVL.
And then you have to find I. Actually, no, you can't. Or
Actually, and your sign is wrong here, right? Because if this is the I that you're talking about here, is this the I here?
should be negative.
That's going to be negative 4I,
Yeah.
negative 6I. But since you know it's 2 amps here, this is one loop, so that 2 amps is flowing around all here. So
Okay.
you kind of know what IC is by inspection.
Okay. So be negative or positive 8.
IC?
Oh, this is 2. So be negative 2.
Uh-huh. So IC is negative 2. And you got to find VL. That's the only tricky one. You can use KVL to find VL.
Okay.
If you're following it this way, it is minus 12 And this is going to be plus, you know, plus 4 times 2 because 2 is going to be going up this way. You know, that 2 is going to be going around there, right?
Plus 8. And then this one is plus 12.
Plus VL, yep.
Plus VL. Then VL equals -8. Okay. So
That's with I going to the right here.
Mm-hmm. Yep.
okay. And then IC is just -2.
Yep.
0.4.
Mm-hmm.
Calculate.
Yep, that's it. Okay. So you got this. That looks good.
Looks good to me.
5VL.
Now let's see if so
There you go. Now you're doing the final values.
going around to -12 plus 4 equal plus 6I plus over 2L equals 0 equals you know what I was. 2L, what's L?
0.25. So 20.
That's all to cancel.
Dude, you're good.
So are you finding the initial values here?
Yeah, we found I naught and VC naught. We found DIDT naught. So we jumped to finding alpha and omega naught
To figure out which case we're in.
and then we also need to find the VDP naught. Or the VDP naught.
Not a 0. Yep. VC is 60 volts. Good.
Isn't that, yeah, we do like a short thing. So that'd be square root of 0.1.
Mhm.
Get the calculator behind.
Yep. So yeah. So when this thing switch, so this is getting a buildup of 60 volts here. And when this switches, you have 0 current because that's got 0 current. Initial value was 0. So there's no voltage drop here. So yeah, the VL. Now, how are you defining the direction of current?
To the right.
That way, right?
Yeah.
Okay.
So passive sign.
Okay. So then, yeah. So plus minus
Yeah.
is going to line up opposite of the 60 volts there. Yep. So you got minus 60 volts. So minus 240 amps per second. Did they define the direction of the I? Oh, actually, wait.
Oh, they did.
That's
Oh no, this
problem.
is it. No, they didn't.
Find V of t. So they're only labeling V of t.
Yeah.
And that's tricky because, yeah, you have to find I of t first. But it doesn't matter why you choose it, you know, eventually. So if you want to define I going this way, which is what you did, right? You define I going this way. And the I for the inductor is also going to be the IC for the capacitor. And since IC equals C dV dt, you could integrate I to find the voltage of the capacitor.
Why do we have to find ISG first?
Why do we have to find I of t first? You know, I think you could possibly, you know, it's just when we do series, the differential equation that drives it, that governs it, is sort of suitable for I. It's easier to define in terms of I.
Right, because the voltage drop could be different for each of them, but the I is all the same.
Yeah, so you get that differential equation, and that's easy to solve. So I think that's why we solve for I.
Oh, you're doing the differential equation part?
Me?
Yeah.
No, I'm just. This is 0. dv of c dt at 0 is 0 because I of c is of 0 is
Yeah,
0.
that's true.
I'm just labeling it.
Mm-hmm. Yeah.
Looks like we're overdamped.
Okay. Looks like that agrees with the solution.
Alright.
So those all worked out okay?
So that means that
Very nice.
I
Nothing going on there, so 0 and 0. Good. Yeah, so
Yeah, it's probably not right. Yeah.
how you guys doing here?
So we're trying to figure out the infinity ones.
Yeah.
So can we just assume that when the switch is open, then the inductor goes to a short circuit, this goes to an open circuit, and like there's nothing here.
Yes.
So there's no current flowing, so there's no voltage.
Yeah, you basically have just a couple resistors floating in space.
Yeah.
In the asymptote, right, when you get to infinity.
So
There's nothing driving it, so it's 0. And basically, if it's a source-free circuit, which it is, it has to go to 0.
yeah.
20 squared minus.
So when we're trying to find like the I plus and everything, or the 0 plus,
Mhm.
that's probably the time to write those things as sources. The inductor
Yes.
and capacitor, right?
Yeah, at the 0 plus, when you're trying to find the derivatives, that's when you want to write them as sources. If you're going to do that. I mean, you don't have to, right? You can just label that as an inductor, but just make sure you got 2 amps going through there. You can label that as voltage source, as a capacitor, and just put plus minus 12 volts there. This is the invariant step. These are the invariants, right? Those are the things that don't change. Those are the only things you know for sure
So we have S1.
at t equals 0 plus. Everything else comes from those.
So can we use that like consistently anytime we're trying to find 0 plus, or
And what do you mean by consistently?
like consistent
Consistently?
in like most problems that we'll encounter? Is that like a
Well, it's only for finding the derivatives, right? For
That's what I
finding
mean,
the
yeah.
values themselves, you're going to use what they were at 0 minus.
no? Yeah, but like the
Yeah, but for all these second order problems, when you're finding the derivatives at 0 plus, you basically could turn these into sources with whatever the values they were at 0 minus. Yeah, it's just another way of saying the same thing. They don't change when the switch changes.
Okay.
Okay.
It's nice to have a consistent
Yeah.
problem solving approach.
Mm-hmm. Yeah, you want to get that anchored because that'll save you a lot.
Yeah, so I'll get one part of my square right now.
Oh, we got hummus. We got more Lauren bars. Salted dark chocolate and nuts. Okay.
So we got a little stuck. So we're doing
Is that 8.1 or no?
8.1, yeah. So
Yeah, you wouldn't put it the other way.
this is what we found at t equals 0 minus, which is when the switch is closed.
Okay.
And that's steady state. So that means that the inductor is an open circuit, the inductor is a short circuit, and the conductor is an open circuit.
Okay.
But from
So
there-
what is this to you? What do you call this?
open circuit?
That's an open circuit?
Yeah.
Now you said that the inductor becomes a short circuit. And which one of these is the inductor?
Oh, did we write it wrong? So the inductor, short circuit, yeah.
Yeah.
Capacitor.
Which one on the, here's the inductor.
Short circuit. Oh, okay, so we mix matched it.
Should be over there, right?
Okay. Okay. So that would mean that this is different.
Yep.
Okay, so yeah, that would be 12 over 6. 2. Okay, but from there, now what do we do?
Well, you got to find IL of 0 plus.
Okay.
Oh, well, yeah, it's 2, yeah. And then what's VC of 0 plus? I mean, really what this is asking you for is you got to find all of these initial values, I of 0 plus and V of 0 plus, find the derivatives and their final values.
I guess I was confused because this is the closest example to it, but it's different because the switch is closing.
That is not the closest example.
No, it's not. Okay.
The closest example to that is this one.
Really? But there's no switch on that one.
Well, no, but I mean, it's the same kind of problem where you got to find the derivatives and the initial values and final values. There's a step function there, which is kind of like a switch.
Okay.
And we only did one of those.
So the first one?
But yeah, it goes through that process of finding
Okay.
those initial and final values. So you don't need to find alpha and omega 0 for these.
Oh, you don't?
No, this is just the initial and final value problems. It's part of the larger solution when you do a real full-up problem, which is the third one on this.
Okay, so I guess my question is, I'm going to go to this.
So now you got to find you found IL of 0 plus?
No,
Now you got to
we
find,
didn't find that.
well, you did. You found it's 2 amps, right?
Oh, I see. I see. Well, no,
Now you gotta find-
0 minus.
And 0 minus is 2 amps, but that's all what it is at 0 plus. So
Okay.
it's basically that's 2
Okay.
amps.
Okay.
But you still have to find VC of 0 plus.
Okay. So IO equals IO. I guess we wrote it there.
Yeah, of 0 plus. Plus, or whatever. Yeah, good.
Mm-hmm. Okay. And then for V, is V the one that has the derivative? To find it, or is this the dVC over dt equals IC?
Not yet.
No.
This is just V of VC of 0 plus.
But how do you find that? This equation.
Well, there's no equation. It's the voltage across the capacitor.
Oh, which is 12. Yeah, because it's
Because you got 12 volts across a 6 ohm resistor. What's the current through the 4 ohm resistor?
2.
Then you're going to have a voltage drop of 8 volts from here to here. So this would only be 4 volts. What's the current through the 4 ohm resistor?
12 divided by 4 is 3.
3. So it's 3. So that means you're going to drop 12 volts here. So the voltage across the capacitor is going to be 0.
Oh,
How is the current not zero in open circuit?
I don't know. He said it was 3
right,
because it's 12 divided by 4.
yeah.
Oh, yeah. Sorry.
Right? Right, David?
Well, I'm just confused how there can be a current with no circuit.
Well, it's current here, not here.
Right? There not be current if it's like that.
Well, the KCL has to apply here and here as
Oh,
well.
wait, yeah, that's true. That doesn't make sense.
So if you have 3 amps flowing here, you got to have 3 amps flowing through here.
So now that we know that the voltage here is, what did we say, 0? You said like 3 different things, so I'm not.
What do you think it is? What's the voltage across the capacitor?
I was trying to figure out the current.
Yeah, what's the current through the 4 ohms? So there's an open circuit. The capacitor is like an open circuit, right?
Wouldn't it be 12?
Wouldn't it be 12? Why?
Because 3 times 4 is 12.
Because 3 times 4 is 12. What do you think, David?
And it's in parallel too with the 12 volt source.
Have you ever looked at a battery which has maybe 2 terminals, nothing hooked up to it, and wondered how much current is coming out of it? How much current is coming out of it? Why? Okay. What if you hooked a resistor like that? How much current? And suppose the resistor is a 9 volt battery. Suppose it was a 1 ohm resistor. Are you going to get 9 amps out of that battery? There's no current because you don't have a closed circuit, right?
So the current at that.
If this was a 4 ohm resistor and this is a 12 volt source, that's kind of like what you have here. with a capacitor that in the steady state acts like an open circuit. What's the voltage across those terminals?
Because like when you did a source transform, you had zero. Yeah.
Why?
Right. Because the current is zero.
Okay.
And
The current here is 0,
V equals.
but so you're just guessing.
I'm not guessing.
Yes, you are. You're guessing, and you're guessing wrong.
Wait, what? You're like leading me in the wrong direction.
I am. I'm trying to lead you in the right direction, but you keep going off course. So I equals 0.
Okay.
What's the voltage drop across this resistor if I is 0? David, what's VR? This is 4 ohms.
Doesn't it have to be zero?
Okay. Now you do KVL for me around that loop and tell me what VC is. Solve it for VC. Starting right here, you're going to have minus 12 plus 0 plus.
So it has to equal 12.
Yeah.
Then why did you? So why did you make me think that it was 0?
I didn't. But you said it was 12 because 3 amps times 4 ohms is 12.
Wait, our original guess was 12. It's a parallel.
Yeah.
12 volts.
That's not what he said.
Originally, that's what he said.
No, it didn't. He said it's 12. I said, why is it 12? He said, why is it 12? Because 3 amps times 4
Isn't it
ohms.
all like connected, like the same rule?
What do you mean? Isn't it all connected to the same rule? It's not something that you can actually analyze.
Isn't it the same in parallel because the current times the resistor is equal to?
So do you still think there's 3 amps going through this 4 ohm resistor?
I'm not learning anything now.
Just yes, that's a yes or no question.
Um,
Do you think there's 3 amps going through that 4 ohm resistor? Because depending on your answer, we have to do something else.
I think that there is 3 amps going to that pharmacist.
Okay, David, how come he was able to get that, but not this? You know him more than I do.
That one's more visual and straightforward.
It's more visual and straightforward.
So you're
Sure.
saying that there's 0.
What's the current through the 4 ohm
there's
resistor?
0 amps going through that resistor.
That's what I'm saying. And you're having a hard time with that. But that is something that, you know, when people do circuits for a while, they get that, and it's stiff, right? You got to get that, because you're going to have this happen over and over again.
Well, that makes sense that there's 0 amps going through there because.
Yeah, but so when I ask you what's the voltage, then what you got to do is KVL. Just like we did right there. It's the same thing. So you're not guessing.
But couldn't you also know that that's 12 volts because it's in parallel with 12 volts?
Could you also know it's 12 volts because it's in parallel with 12 volts?
Like a rule or law?
Yeah, as long as you don't think that there's 3. I mean, if you think there's 3 amps going through here, then the voltage has to be 0. Because you're going to have minus 12 plus 3 times 4 plus VC equals 0. So then you get 0. Conceptually, this is going to screw you over if you don't get this, right? A dangling resistor going into an open circuit has 0 amps going through it always.
That is what I originally thought, but then you made me think something else.
I didn't make you think. I asked you a simple question.
No, I do agree with you.
Now I get it. Now I get it.
Guess 12.
You guessed 12,
You did
but
guess 12, but it
it's
wasn't
okay if you
because
guess
of the
12.
4 times
But if you guess 12 for the wrong reason,
So
that's still a mistake.
So there's no current going through the dangling resistor.
That is correct. Yeah. And that is a conceptual thing that has to sink in for you to be able to do these kind of things.
I understand that.
Okay.
But my question would be, why would there be 12 volts there if 0 times 4 is not 12?
Why would there be 12 volts if 0 times 4 is not 12? Well, don't you believe in KVL?
I do.
Well, that's your answer. Okay.
So now we have the voltage there.
All right. Now you got to do the other ones. The other ones, the derivatives are the hardest ones. How's it coming? You got I okay?
Yeah, we got it.
Awesome.
Yeah, so we just need to rewrite it. So remember,
Yeah.
there's a constant, the initial conditions.
Yep. But the initial condition was that it has to be 60, right?
Yeah. So yeah, so 64.6 for the first one, and then yeah,
What's the second one?
4.64, 1, 2, whatever you want.
So we found the initial conditions. Very good. And found alpha and omega 0.
Is that it? Oh no, we have to.
Plus initial condition
On the initial.
is 60 volts.
Zero has to equal
Oh.
60.
What if we VC is 0? Yeah.
Well, look, when we add these together,
No, we can't.
no, when it's 0,
Yeah, when you add them together, it equals 60,
it
right?
equals 60. So K has to be 0, but we have to show that.
But doesn't VC have to be minus 60?
No, VC is positive.
Oh, VC is positive 60, yeah.
So then,
But why is there a 60 in the answer here? Do I have to change that?
No, it's the initial condition.
Is the initial condition 0? Wait.
no.
No, it's supposed to be 60, but see, when you add this together, the initial condition is going to be 0. Right? I mean, it's going to be,
Oh,
it's going to
yeah.
add up to, actually, it's going to add up to 120, right?
So when we add this as K, then what's going to happen is BC of 0
Yeah.
equals 64.65.
You know, I did this last, there was one of these things that had an
Minus-
error in it, and it might be this one.
Yeah, so the 60 just isn't
Yeah,
there.
I fixed it.
Fixed core. No, this works. This works. Plus K has to equal 60 volts,
Yeah.
right?
Yeah.
So when these go together,
Yeah.
we're gonna VC of 0. Oh no. We get 60 volts equals these added together. That's gonna be 0.01, which might as well be 0.
Yeah. Okay.
It's probably rounding errors that we did.
Mhm.
And so then that would just leave you with K. K equals 60 volts. And then,
No, K, because this is 60. So you have 60 plus K equals 60.
oh,
So
duh,
K must be 0.
I have 60 plus K equals 60. Therefore,
Yeah,
K equals 0. And so everything worked itself out in the end.
Yeah.
So
but
then-
there's an error in the thing. Let me see if it's in the,
You did something wrong?
well, it doesn't agree with the answers.
Oh, crud.
But that doesn't mean that the answer is not, it couldn't be wrong.
So,
Let me pull up the solutions.
So what does the answer say? How far are we off?
it says it's 60. It says plus 60.
That would imply that the initial value is 120, and that can't be right. It's got to be 60.
It seems like it.
But typically, when I run into these, I fix them so they don't come up the year after. Remember, this thing happened before. What problem is this? 817.
Wait, look at
Yeah.
I did take a look.
No, because if you turn it.
Since, oh wait,
Yeah.
wait, okay. V of C, V of T equals 1 over C times the integral. Wait.
not like connected. Oh, you're actually going.
Well, you know, this is interesting. Here's the solutions, and I think they still have a mistake in them. But look at the reasoning, right? They say, you know, your I is this. You got this for I, right?
Yeah.
And then d of t equals 1 over c times the integral from 0 to t of I dt plus d of 0, right? Because this is integrating the charge that you're getting onto the capacitor from I. Right, the integral of I is giving you the charge.
But when the
No, the thing is, it's the integral. No, it's the integral from 0 to t. And when you're doing that, that becomes a definite integral. So you did an indefinite integral with k. When they integrate from 0 to t, you got to plug in t here, but then you got to subtract out when t is 0, right? It's a definite integral, right? So the mistake that they made is it should be, you know, 60 plus this is the integral with t in it. Then we got to subtract out this I, or the integral of I, with 0 for the exponentials. So in other words, you plug in 0 in there, and that subtracts out 60. So that's what they forgot.
Oh, that's really clever. I like that.
Yeah.
But it's too bad they messed it up.
Too bad they messed it up. Yeah.
Oh, alright, so they made it a definite integral.
Yeah, because physically, what's controlling the voltage is the additional charge that's dumping onto the capacitor between
But they're
time
not
0
integrating
and
the
t.
60 though, right?
No, it's 60 plus the integral,
Right.
60 plus 1 over c to the integral from 0 to t.
Right, that makes sense because it's the initial condition.
Yeah.
Right.
Yep. That's why the dt is over here. If the dt was over there, then they would be integrating to 60, but they're not. So I do need to change those. I never get time to change all the errors. I know there's some mistakes from Java I can get to, but whatever.
Okay.
Yeah, so you got the right answer. I'll have to strike that 60 out of there.
DI, right?
Yeah.
Or IC, the same as IL.
Is IC the same as IL? For t greater than 0?
For T less than 0.
What you should do is, for t less than 0, no.
Wait,
For t less than 0,
no, greater than 0.
Oh.
yeah. For t greater than 0, well, you got to draw the circuit. If this is, you know, draw the circuit again for t equals 0 plus, right? You got that switch in there, so let's draw the circuit with,
So this is when
the switch is open. See, all these questions are easy to answer if you just redraw the circuit. And now this is t equals 0 plus. You can't use a capacitor anymore or a short for the inductor or an open for the capacitor. So that's IL. This is VC. What did you say? Is IC the same as IL?
IL, does IL equal IC?
Okay, and what's the answer? No, why not?
Because it's one for the inductor, one for the capacitor.
What?
IL's for the inductor and IC is for the capacitor.
Well, how would I draw IC on here, Isaac? Okay, David, is that right?
Not according to passive.
I draw it according to passive sign convention.
Oh, because it has to.
Now, Isaac, label VL on the inductor.
VL?
Yes. With the right polarities?
Because that's the current that can't shop.
Yeah, passive sign, passive sign. Okay. Is IC the same as IL? Yes? Okay.
Wait,
I don't know.
would it be opposite?
Would it?
It's going into the same. Wait, no, because
Can you do KCL right here?
at A.
Yeah. If you do KCL at A, what are you going to write?
No, because they're both coming out of it.
So VC naught is a no jump.
Sum of all the currents entering or leaving a node equals 0.
Those are two things paired out.
I guess if those are the those are the length of currents.
That's why you have to
to
find
be opposite.
because you know that they can't.
But they're both coming.
Like these, IC can or VL.
I think
So-
I'm getting confused because they're like they roll with it's going in, if it's negative, it's going out, positive.
Yeah. You guys, you got to get over these things. You
But
can't be thinking about this on the next test. This has to be automatic. This is stuff we've been doing since like the second week of class.
So if they're both coming out of it, then how do we know which one is positive and negative?
So what this says is IL plus IC equals 0. So
Either one.
IL equals minus IC.
Yeah, for 0 plus.
How do we know which one's positive, which one's negative? Well, we know actually at T equals 0 plus, the other thing that's going to be true is IL is going to be what? And VC is going to be what? We know what these are, right? At T equals 0 plus, IL is going to be what?
Zero. Right.
It is? Why?
0 plus.
Yeah.
So it's gonna be like a.
What does that say right here, though?
Now we open up to
Yeah, so wouldn't it just be like having no voltage source there? Or a current source?
Oh, because
It'd
it's
be like
equal to
having
0 plus.
Why?
So because that's
With no jump roll.
no jump. Yeah.
So it should.
I wrote it.
It should look like that though.
Good. Great. Too bad you didn't remember it. Okay. So IL is going to be what?
So it's a short when T is like, you have something, it's a steady state. When it's a steady state, it's short. And that's so this is not a steady state. This is that
Two?
one steady state.
Oh yeah, no, I know IL. I was asking
Okay.
about IC.
Oh.
Okay. So what's IC going to be?
Negative 2.
So.
Okay.
No,
What's VC going to be?
I have zero, you already said.
Well, what's VL going to be, actually? That's the big question. No, actually, we know what VC is too, right? What's VC going to be?
Make that impossible, it has to be-
Okay.
Oh, okay. I see how this works.
Yeah, those are all the pieces. Now, in order to find the derivatives, which is what we're doing here at 0 plus, right, you got to find DIL dt of 0 plus.
I don't know, like, how important.
What does that equal?
you can draw that. But basically, what's important is to find I of 0 minus, I of 0 plus. You find,
Well, what's the inductor law? Yeah, it's VL over L.
yeah.
And what's dVc dt at T equals 0 plus? Okay. Well, you pretty much got that one because you know what IC is. You just divide that by C and you're going to get the answer. But to find VL, you're going to have to do a little more work, right? You got to find VL using probably KCL. You know the current, you know this voltage, that current, you can find VL, it's the unknown. So set up KVL and solve for VL, and then divide that by L. That's going to be the derivative of your current.
So in this case, since the voltage across the capacitor is in parallel with the voltage across the inductor, why isn't VL equal to 12?
Because that's not the definition of parallel.
It's not.
Here's the definition of
Oh,
parallel.
because there's resistors? I see.
That's parallel,
Okay, got it.
okay? Yeah.
Ask me for a friend.
Okay, how's that coming here? This is a real fun one, right? Oh, you're just making steady progress.
She's slowly taking over the whole board.
She is, and it's with such a nice, neat
Yeah.
handwriting. Hong, you are going to rule the world someday. But it will be an orderly world. Okay.
Yeah, I get why I went with 0.
You know, if you are, yeah, no, that's right. But this k should be v of 0. If it's, I think if you take off the limits, it's just any old k, and you can figure that k out later. But you know what that k is if you're doing a definite integral. Because the voltage at t0 started at some value, and then you got some additional charge added or subtracted, so that changes the voltage.
Yeah, so that's interesting. So like the fact that you're saying it's going from 0 to t,
Yeah,
is forcing you to recognize that, well, if you went from 0 to 0, this would have to be v of 0.
yeah,
But if you get rid of these,
exactly.
then you're not saying that.
Right.
That's weird. I
Yeah.
never thought about that.
Yeah, it's very cool. And that's why you are doing the right thing here, because you're subtracting out. Is this the value when both of these are 0? You get that? You're adding this and that together gives you that? Oh no, they got to multiply by x equals 5. Yeah, okay. So this is basically 1 over 2.679 minus 1 over 37.32. Okay. Yeah, that makes sense. Yep. So 60, 60 right there.
So now we know L 0 plus.
So that is 240.
Welcome back. Thanksgiving that.
Still kind of lost.
How so? Where are you
So
lost?
we found VL 0 plus,
Uh-huh.
and then we found VC of 0 plus.
Uh-huh.
So we just found DI 0 plus over DT.
Yep.
And it's just continuing from there.
Uh-huh. You know alpha and omega 0, so it's overdammed. You found the two roots. And so this is the point where you throw it all together.
Plug it all
So you've done all the hard work, and it's just combining it all. So I of 0 equals 0 amps. Yeah.
I guess there was no C.
Yep. And that equals A1 plus A2. Okay. And then di dt at 0 plus is that, but it's also, you take the derivative of that solution, you're going to get an A1 times this and A2 times that has to equal minus 240. That's another equation you can solve for A1 and A2.
Oh, okay. We can solve what A1 and A2 equals.
In the solution,
Uh-huh.
you have the extra.
Yeah, there's an error in the solution. Yeah. So since it's time to go, you can, if you want to combine, Hong will give you an overview of 817. That's what it's all about, really.
Is the error the 60?
Yeah, you scratch out the 60 constant there. It goes away. And Hong will explain why. I won't film this. No. Oh, you're going to be ruling the world someday. You have to be able to stand in front of the camera. No. You rule the world from behind your computer monitor. Yeah, isn't that amazing?
With nice handwriting.
So here's the here's that equation that you would do with the derivative, right?
Right. Yeah, it's just a 2.
And you solve those, and you get this and this. That gives you I,
Then you have to enter.
which you then have to integrate.
Whoa.
But the integral is 1 over c times the integral value of t from 0 to t plus the original value t0. So this integral is taking into account the additional charge that goes onto the capacitor, which changes the voltage from its original value.
Right.
And the integral gives you this, but then you still have to, this is what the mistake was in the solutions, they didn't evaluate it from 0 to t, they just dropped that. And so they had a 60 at the end. But that 60 goes away because when you evaluate this from 0 to t, what you end up getting is this is the value at t,
Yeah.
you get a minus this value at 0. Well, this value at 0 is, you know, this is 1, this is 1. It's 1 over 2.679 minus 1 over 37.32 is minus 0.3465. So you multiply that times this constant, and that turns that thing into 60.01. Yeah, so it basically cancels out that 60, so you end up with just this.
Wow.
Yeah.
What a process.
Yeah. Yeah, look at that, huh?
So yeah, I'm kind of confused as to why this, like the IL here.
And you have to be able to do this on a test, you guys. And you're confused what?
Why is the IL the?
Well, that was an inductor here.
Yeah, yeah. So Mason was explaining it to us, but I'm still kind of lost on like why the like why did we label IL here? Because we have to solve.
Well, why did we label IL for the inductor, or why did we solve for
Are
IL?
we trying to find the?
Yeah, we're trying to find the voltage of the capacitor, but this is a series RLC circuit, and the ODE that you generate from a series is involving current.
Right. Oh, okay.
Because they all have the same current, so you can write the ODE really easily. You might be able to do it. I don't know that you can't do it for voltage for a series RLC, but you know it would probably be the same form, and sometimes you can kind of do it, but the method, the technique that we've kind of developed all revolves around finding I for series and V for parallel.
And we write IL instead of IC because we care about the no jump condition for I.
Right.
Yeah, IL is the one that's constrained by the no jump condition. IC is not.
So it comes from the fact that we're also the DE that we get is for the current.
Yeah.
Since it's a series.
It's a series you focus on current.
Okay.
Yeah.
And the no jump thing.
So in this, we didn't have to find dVdt.
No, you don't have to find dVdt. But you could have. And it's not clear to me if you can't just find the solution. You know the form of the solution. If you know V0 and dV, you could probably go straight.
Oh,
you could probably go straight to V.
That's a good point.
The solution in terms of V.
Yeah,
Right?
if you know.
The solution has to be of the same form, right? And you know. So. You know, the solutions key does it that way too, but I don't know why you can't do it in terms of V. I think you probably could. But the, you know, the series RLC makes it the R over 2L, you know, that defines the alpha.
Right.
So they have to add up to 60, which they do, and the derivative has to be, yeah, I think you could do it straight with solving for V straight.
Yeah.
Because they all have the same form. It's all exponentials, right? Yeah. You have the handouts? You're taking them over? Okay, thanks.